Okay, hello everybody. Welcome back to the MIT Category Seminar. Today we are very happy to have Eugenia Cheng. She's a celebrity. Many of you know her, so it's uh, it's really nice to have her here. I also see a lot of new faces, so welcome to all the people that were not here before. Please keep in mind, of course, that this is a math seminar, so please let's keep the discussion on topic. And Eugenia is going to talk about distributive laws for Lawvere theories. So many of you may know distributive laws for monads. So we're going to see a version for Lawvere theories that is published in compositionality. So hello, Eugenia, and if you want, the mic is yours.
Thank you very much. Everyone, wave if you can hear me, just so that I can. Okay, yay, hi everyone. Well, thank you very much to Brendan and Paolo, especially for inviting me to give this talk. And thank you all for being here. If I keep looking up to the left, it's because I've got my desktop screen over here with all your lovely faces on so that I can see that there's people here. I hope that everyone is doing all right under these circumstances. It's obviously a very tragic world situation that we're in, but there are some benefits that we can get from this, that we can lead into from this situation. One of which is, now that we're all giving online talks, the talks are available for everyone all around the world to see. So I'm glad that there are many people, and presumably many people, who aren't actually at MIT and who wouldn't have been able to come if this had been a talk in person at MIT. Though obviously I miss giving talks in actual person. There's also some drilling outside my apartment, so I apologize for that. I'm going to talk about distributive laws for Lawvere theories, and this paper was recently published in Compositionality, and I would like to thank everybody who founded and runs this new journal. I think, as some of you know, I believe in completely overhauling the journal publishing system in many ways. I think the journal publishing system has many flaws, and I'm very hopeful that amazing, energetic people will be changing things in the future. So this paper is, in fact, the work is rather old. And so this has presented me with some challenges, because even in the normal lifespan of publishing something, to give a talk after it's published would usually actually be quite a long time after you've done the work. And this has been a particularly long time. So I first presented it, I think, in 2011, which really is a long time ago. And so whether I can still understand any of it is an interesting question. But what happened is that I submitted it for publication somewhere else, and I got a referee's report that was, I felt, really very obstructive and unconstructive. And I was going through a time in my job in Sheffield where I felt generally obstructed by everyone around me, and I felt like I wasn't supported, and I had 3 referees reports at the same time that all seemed to be obstructive, and I really didn't have the ability to deal with it. So that was roundabout when I changed my whole life around. I quit my job in Sheffield, I moved to Chicago, I wrote some other books, and then a lot of time passed, and I couldn't face dealing with that report because it had really traumatized me. And so clearly, de facto, that I had withdrawn my paper from that journal, and then compositionality came to exist, and I thought, okay, I will try again, with the added benefit of supporting a new journal. And that's really what gave me the impetus to resubmit the paper, because I am not someone who is very good at just working through my fears. So the idea that I could maybe support a new journal to help overcome this traumatic referee report happened. Anyway, so that's the story of why this took quite such a long time, and why there's a version out there that has existed since 2011. This is not extremely different. It has been improved by some refereeing, so I'm grateful for that. But if you have read the paper a long time ago, then it's really not very different. But there are people around who weren't in the field then, and I appreciate the opportunity to speak about it again, because I do really love this work, even if I look back on the proofs at the end and I think, crikey, did I really do that? How did I do that? I don't know. So I have been encouraged to make this somewhat expositional. So I will focus more on the exposition of setting things up and less on the details of the proof, which also helps because the details of the proof for me are a little hazy. It's in the paper. I read the paper last night and thought it was a good proof. But anyway, so here is the plan for the talk. First, an introduction to what the point is of all of this, and an introduction to Lawvere theories, and an introduction to distributive laws for monads. So obviously none of that is new. And if you're an expert, therefore, feel free to turn your video off and have a little nap or do something else. Or you know, leave your video on and have a little nap. That's been known to happen too. So then I will give actually 3, well, maybe even 4 definitions of distributive law for Lawvere theories. And they will give different points of view. And then I will do a comparison. So what I do at the end of the paper is prove senses in which they're all equivalent. And as usual, having many things that are equivalent does not render any of them redundant. What it does is give different points of view for different purposes. And as is often the case in category theory, and particularly in my work, there's one version that's particularly abstract and one version which is much more nuts and boltsy. And then it's really helpful to have a way of mediating between them, because the abstract one is really good for generalization and theorizing. And the nuts and boltsy one may be better for actually understanding what's going on. But then what's important is to have the abstract one and also the nuts and boltsy one, and also a way of understanding the sense in which they're equivalent to each other. So this work was prompted by Jean Benabou, who asked me if I knew how to do this. Because my previous work, I'd given a talk at the 89th PSSL on iterated distributive laws for monads, and Benabou said, why hasn't anyone done distributive laws for Lawvere theories? And I didn't know why no one had done it, and I didn't know if anyone had done it. It didn't seem like anyone had done it. And I hadn't done much work on Lawvere theories, but since Benabou asked and I had an idea of how to do it, I then did it. So that's how this work came about. And it shows one of the wonderful things about giving talks where people get together and have ideas and ask questions. So I will attempt to stop periodically and say, does anyone have any questions? And so, in fact, does anyone have any questions?
So, by the way, if you have questions, please write them in the chat, okay? You can also use the chat of YouTube if you're following us on YouTube.
Right, and so I think what's going to happen is that if there are questions in the chat, then Paolo will speak the questions to me out loud, and I'm not going to monitor the chat as I go along. Okay, good. So the idea of distributive laws is that they give us a way to combine 2 or more types of algebraic structure, typically expressed as monads. And so the basic motivating case that we are usually familiar with from maybe high school, even if we haven't thought of it that way, is that if you combine the structure of a monoid with the structure of an abelian group, you get a ring, as long as the 2 are coherent enough. And the coherent enough part comes from the distributive law, the usual distributive law of multiplication over addition. There's a sort of curious aside, which is that you don't actually need the group to be abelian because it follows afterwards. But that is a motivating case. And so then the question is, what's a distributive law for Lawvere theories? And here is a little schematic diagram. So the idea is that Lawvere theories correspond to particular kinds of monads, which are the finitary monads on set. And I'll talk more about what those are, but they are basically the ones that are entirely determined by their action on finite sets. So Lawvere theories can be defined in various ways, but there's an abstract point of view which says that you can express them as monads somewhere. And then the idea is probably that distributive laws for Lawvere theories expressed as monads should correspond to distributive laws for the corresponding finitary monads on set. And so then the question you might ask is, if they're the same, what have we achieved? And there are some people who think that if you show that some things are the same, then the thing to do is just ditch one of them immediately. But I don't think that's the case, because first of all, you get different points of view. But secondly, one of the points about Lawvere theories is that you immediately get algebras in other categories, which is not what you do if you're doing monads. So a monad on a category V only gives algebras in V, whereas a Lawvere theory then gives models in any finite product category. And so here is a little schematic diagram that I made, where the top level of this cylinder is the theories, and the bottom level of this cylinder is the algebras or the models. And my idea is that Lawvere theories as finitary monads give you this little cylinder where you immediately get only a certain kind of model in the same category that your monad lives on. But then as Lawvere theories, the models, you get more models because you can take models in many other categories. So for example, if you do monoids over abelian groups just as monads on set, all you get is rings. Whereas if you do them as Lawvere theories, you can put that in any finite product category. So you can get rings in other places. And that gives you more richer possible structure. Does anyone have any questions? Okay. So here is the idea of a Lawvere theory, which is that we encapsulate an algebraic theory in a category, and the category encapsulates the arities and the operations. So the arities are going to be the natural numbers, and a morphism from k to 1 is an operation of arity k, and then a morphism from k to m is m operations of arity k. I would just like to say that some of your screen pictures on your profiles are really attentive, and it's really funny because every time I look around, I think, oh, wow, people are really paying attention. And I realize you're also not moving. So what we actually do is we use a skeleton of finite sets. So this is like the category of finite sets and functions. And the skeleton means that it's quite a lot like the natural numbers because it's just the number of elements per set. And a Lawvere theory is then a small finite product category equipped with a strict identity on objects functor from the opposite of this F category to L. And so I would like to just put in a caveat that there's a lot of op issues in this work. And my brain exploded when I tried to go back to the op issues from the paper and sort them out. And so I've just decided to gloss over them almost completely. The one that's really clear is that the finite sets is made from coproducts. So when you take the opposite, those coproducts all become products. And that's why this is a finite product category. Later on, I start dealing with categories of spans and profunctors, where there are all sorts of different directional conventions you can take. And I will fully admit that I'm glossing over those and that I do them right in the paper and not necessarily in these slides. So in F-op, M is the product of M copies of 1. In the category of finite sets, an M element set is a coproduct of M copies of the 1 element set. So we've turned everything around and we're doing finite products now. Does anyone have any questions?
Yes, there is a question.
Mm-hmm.
Someone is asking, what does it mean to have an identity on objects functor between different categories?
Oh, so really it means that you've got the same object on both sides and that the functor does the same thing, that leaves the objects as themselves. So thank you for that question. That means that F has as objects basically the natural numbers, and that L also has as objects basically the natural numbers, and that nothing happens on objects. Are there any other questions?
Not for now.
Okay, great, thanks. So one feature of Lawvere theories that is a bit different from some other types of theory is that we are allowed to forget and repeat variables. And this is different from, for example, if you express a theory via operads without symmetric actions. So in the theory of monoids, if you have two basic objects A and B, the operations of arity 2 in the theory of monoids, there's just A, B. That's the only thing you can do with two objects. Whereas in a Lawvere theory, it's all of these things involving A and B. So in other words, it's everything in the free monad on A and B. And so you can view this as counting operations differently, or you can view this as counting arities differently. But in any case, something is happening a little bit differently. The outcome is the same for the theory of monoids, for example, but the way that you express it is a bit different. And so, for example, in the Lawvere theory, a morphism from 3 to 2 is 2 3-ary operations. And so in the one on the left, AB counts as a 3-ary operation, even though it only involves two things, and so does A cubed. But you can also have ABC, which involves more obviously 3 things. And then when you compose in this Lawvere theory, so this is a composite from 3 to 2 to 1. So I've got from 3 to 2, I've got 2 3-ary operations, and from 2 to 1, I've got 1 2-ary operation, and then the result at the bottom is 1 3-ary operation involving A, B, and C. Does anyone have any questions about that? Okay. So there are many possible expressions of what looks like the same operation. So for example, the operation ABC could count as a 3-ary operation, or it could count as a 4-ary operation where we've just forgotten about the fourth variable, or it could count as a 5-ary operation where we've forgotten about the fourth and the fifth variables. But they're all related by projections in F of. So the diagram on the right there shows that all of those things commute via the dotted arrows, which are kind of inherent to F. So they're not really something extra to the theory in particular. There's some feature about Lawvere theories that just says you are always allowed to forget variables and also repeat them. Are there any questions about that? Okay. So that's just the definition of Lawvere theory again, because now we're going to talk about a brief thing on generalization. So there are various generalizations. Here are a few generalizations. You could use the whole finite sets instead of a skeleton. There's something we're going to come back to in the most abstract approach, where if you use the free finite product category 2 monad, then you note that the category of finite sets is f of 1, and then you could do f of something else to get types in your theory. So we will come back to that approach. You could just say that a Lawvere theory is any finite product category, and then you'd have different types of arities, and you could do finite limits instead of products. So there are many possible generalizations, which we won't talk that much about. But what we will talk about is models and algebras. So a model for a Lawvere theory L, you take some other finite product category, and you look for models inside there, and it's just a finite product preserving functor from your Lawvere theory into that other category. So here's the idea that on objects, right, our Lawvere theory just has the natural numbers as objects. And so the natural number 1 gets mapped somewhere, and that's the basic underlying data for our algebra. And then the object k, well, k is the product of k copies of 1. And so it's going to, because it's finite product preserving functor, this is going to have to be mapped to a to the power of k. And so a to the power of k is now k, if these were sets, it would be k elements that want to be evaluated somewhere by an arity, by an operation. So then on morphisms, a morphism from k to 1 is an operation of arity k. And so what that gets mapped to is a morphism in C from a to the power of k to a, which is evaluating the operation as an actual element of the underlying data. So that's an operation of arity k. So if this were sets, then for example, we would have a string of k elements, and we would have an operation of arity k. And what this model would tell us is how that operation actually acts on those k elements to produce a single element of a back again. Are there any questions about that?
So there's a question somebody's asking, could you, what does it mean on the left part of the slides in the definition of Lawvere theory, what strict means? If they're asking if that means product preserving.
Yes.
Is it strict monoidal?
Yes. Thanks.
Okay, thank you.
Okay, so here's how Lawvere theories correspond to monads. The idea is that in a Lawvere theory, an operation of arity k is expressed as a morphism from k to 1 in that Lawvere theory. And what we were saying, what I said informally on the previous slides, is that that corresponds to a k-ary operation is an element. You take the free monad, the monad on the set of k elements, and that's what the operations of arity k are. But an element of T of k, so T is a finite tree monad on set, an element of T of k is the same as a function from the one element set into T of k. And then k, a morphism from k to m, we said that's m operations of arity k. Well, m operations of arity k is m separate elements, well, m elements of T of k. And m elements of a set is the same as a function from an m element set into that set. And that is the same as a morphism from m to k in the Kleisli category of T. Because in the Kleisli category of T, a morphism from m to k is a morphism from m to T of k in the underlying category. So now we get that a morphism from k to m in the Lawvere theory is a morphism from m to k in the Kleisli category. And that's how the correspondence goes. So Lawvere theories are related to monads via the Kleisli category and some op action. So the definition is like this, that given a monad T, you get a related Lawvere theory out by taking the full subcategory of the opposite of the Kleisli category, and the objects you're taking as your objects are just the finite sets. And then you can go in the opposite direction. And if you start with a Lawvere theory L, you get a related finitary monad, because you already know what the action is going to be on finite sets. And then you extend it as a finitary monad. And finitary monads, the action on all sets is always determined by this coend, starting with the finitary set, which basically says if I have an infinite set, you look at all the ways of mapping into it from the various finite sets and make sure that you're doing it coherently. And so this gives a correspondence between Lawvere theories and finitary monads on set. Are there any questions about that? Okay, great. So moving on to distributive laws for monads, which is one of my favorite things. The idea is if you're given two monads on the same category, can you combine them to make a composite monad? And the idea is that you've got two different types of algebraic structure and you want to combine them in some kind of coherent way. And the key inside here is how are you going to do, how are you going to do multiplication, right? To do multiplication, if TS were going to be a monad, you would need a way to get from TS back to TS for the multiplication of the monad. And you could try and use the multiplication of T and the multiplication of S separately, but your T and your S are not quite the right way around in the middle. So you need a way to switch them over in the middle so that you get TTSS, and then you can use the individual multiplications to get back to TS. And so it's kind of like saying TS says, because we read backwards, TS says that I'm going to make S structure, and I'm going to kind of make T structure on top of it. And then if I do it twice, then I've got a sort of layered sandwich where I've got S structure and then T structure and then S structure and then T structure. And the layers can't get past each other. So I need a way to switch the layers over so that then I can combine them. And that's exactly what a distributive law does. So a distributive law of S over T is a natural transformation from ST to TS, satisfying the obvious axioms, as category theorists like to say. And the obvious axioms are that it's got to interact sensibly with the multiplication for S, the unit and multiplication for S, and also the unit and multiplication for T. And the classic and beautiful paper of Street, The Formal Theory of Monads, says that you can do this inside any bicategory, not just the bicategory of categories, functors, and natural transformations. And then I also iterated this to say how you can combine n monads with distributive laws and a Yang-Baxter condition. I'll go into that a little bit more in a second. Are there any questions about that? Okay. So key examples, monoids plus abelian groups gives us rings. Then two categories you can get from horizontal composition and vertical composition. And then you can get n categories by doing composition along bounding 0 cells, composition along bounding 1 cells, composition along bounding all the way up to composition along bounding n-1 cells. And that was the reason I was doing iterated distributive laws, because so much of my work is about n categories. So I'm just going to go into, I'll go into those a bit more in a second after we've done the key theorem of Beck, which is that the following are equivalent. A distributive law of S over T, a lifting of the monad T to a monad T primed on S algebras, and then you always have to get these things the right way around, which is S and which is T and which is on algebras and which is on Kleisli. Personally, I cannot do it unless I use the letters S and T. And if someone tries to do it using T and S the other way around, I'm completely confused, can't cope. So it follows, oh right, so we also get an extension of S to a monad on the Kleisli category. And then it follows that TS canonically acquires the structure of a monad. And here's the wonderful part, which is that the algebras for TS are the same as the algebras for the lifted monad. So that gives us two different points of view on the combined structure. We can either look at a composite structure, or we can lift one of the monads to the algebras of the other and find that that gives us the same thing. And something analogous is true for the Kleisli categories. So the first example of rings, right? So S is the free monoid monad, T is the free group monad, and lambda, the distributive law, is the usual distributive law for times over plus. And then what we get for TS is the free ring monad. So the distributive law natural transformation, the component is this. So on the left, we have ST of A, and that is a product of sums, right? So it's an element. You start by taking the free group, and then you take the free monoid on the free group, and so it's S of T. And on the right, we've got a sum of products. So it's in the free group on the free monoid. And if you can't remember which way around is which I never can, you can every single time write it out and think through it again. Or you can remember this fantastic mnemonic, which I will implicate Tom Leinster in this because he pointed this out to me, which is that T is for sum and S is for times. And so the free ring monad TS, what the lifting thing tells us is that we can lift T to a monad on S-alg. So in this case, S-alg is the category of monoids. So what that's telling us is that we get a group monad on monoids. So that if you have a monoid, you can make the free group on it. And what this distributive law is telling us is that the free group on a monoid is itself a monoid because you can define multiplication on the free group via this distributive law. Because you go, oh, well, I've got these formal sums, A plus B and C plus D. I would like to be able to multiply them. How do I do it? Oh, I can use this distributive law. Are there any questions about that? Okay. So the two categories example is that we start with the category we're working in is the category of two graphs, otherwise known as two globular sets. So you've got 2 cells, 1 cells, and 0 cells. S is the monad for composition along bounding 1 cells, otherwise known as vertical composition. T is horizontal composition, and L is lambda is the interchange law. So the interchange law says that on the left, what we've got is a vertical composite of horizontal composites. So that is indeed S of T. And on the right, we have a horizontal composite of vertical composites, which is T of S. And by the way, I didn't say this for rings, but could have done, which is that this is directional. We can't go backwards. And it's very clear that it's not, we can't go backwards, because if you think about T of S here, you can take horizontal composites of vertical composites that don't line up, because the first one could have 5 vertical things vertically composed, and the next one might only have 2. And then there isn't a canonical way of re-expressing that as a vertical composite of horizontal ones, because there's different numbers of cells on each side. Whereas from this way around, if you take a vertical composite of horizontal composites, the composability condition on the vertical composites ensures that you have to have the same width of 2 cells, which means it has to be able to be re-expressed on the right, the other way around. So TS is then the free 2 category monad, and expressing it as this composite of monads tells us that you can build free 2 categories from a 2 globular set by first making the vertical composites at the top level and then making all the horizontal composites. But the equivalence with the lifted monad tells us that this is the same as lifting the monad to S-alg. Now, S-alg here is graphs enriched in categories, because S builds vertical composites, which is just composites of 2 cells. So it's making a category at the very top level. And so S-alg is graphs enriched in categories, and the lifted monad is taking free enriched categories. And so this is telling us that you can define 2 categories as enriched categories, enriched in cat, or by building the composites step by step, starting from the top level down. Are there any questions about that? Okay. So the iterated version is that if you have n monads, and if they're all in a row, and they all distribute one past the other in order, together with a Yang-Baxter equation. So this is quite typical. Whenever you're switching the order of 2 things, if you want to extend it to n, you need to figure out what's going on with 3 things, and then it will extend to n. And so there's a Yang-Baxter equation for any 3 monads in a row, which is this usual hexagon that appears in the definition of a braided monoidal category. You can, of course, express it as braid diagrams, which may or may not be more intuitive. So as an aside, many of these diagrams in this kind of work get expressed as string diagrams, which some people find more intuitive and some people don't. I personally don't find it more intuitive. But the real problem for me is that I'm typically about to go into higher dimensions. And when you go into higher dimensions, the string diagrams don't have enough information in them because, for example, if I need to put a cell at the next dimension up when it goes weak, I need to put isomorphisms or equivalences in everywhere. And I really need to see where the naturality and the associativity is happening so that I can put those coherence cells in. And the power of string diagrams is that it sort of glosses over that so that your eye can see past it. But then if you actually want to see them, then you need to have some way of seeing that they're still there. Anyway, this Yang-Baxter enables us to do things like N categories. And what it does is it makes the composite N thing into a monad. And an example is strict N categories. So you can make the monad for N categories by doing composition starting at the highest bounding dimension and working your way down. And there's interchange for every lower bounding dimension over every higher one. So I learned this from the appendix of Tom Leinster's book, at this point I should say, of the appendix of Tom Leinster's first book, and where he did it one by one. And then if you just decompose it, you get a whole string of N monads. And the reason I was doing it was to generalize it to Trimble's definition of weak N category, which isn't a strict thing, but interchange is strict. The weakness is embedded in the action of an operad at each dimension. So then you can break it down into dimension by dimension operad actions and a strict parameterized interchange. Are there any questions about that? Okay. So here are 3 definitions of distributive law for Lawvere theories. And here is a point of view that I've already touched on, which is that the monad TS says that we can express all structure as S structure followed by T structure, because we're reading from right to left. And the distributive law says if we had it the other way around, we could switch it over. And so for Lawvere theories, what we want, if A and B are Lawvere theories, we want a way of combining them to give a category BA, which corresponds to a distributive law of monads of the associated monads. So if you've got an associated monad TA and TB and a distributive law, what we want is for the composite monad TB-TA to be the same as the monad for the composite Lawvere theory BA, which starts looking an awful lot like some kind of monoidal structure at a higher level, which is what it turns out to be. So here are my 3 approaches, basically. The first one involves factorization systems and is inspired by some work of Rosebrook and Wood. The second one, so then there's a kind of bridging definition because factorization systems can be expressed as distributive laws inside somewhere else, spans, and that's related to profunctors. So then we go via profunctors and then we go to monoidal. Oh, my internet connection is unstable again. I'm gonna kind of plow on. So we get monoidal profunctors, and that's inspired by Lack's work composing props. And then finally, the very abstract one is using the Kleisli bicategory of F on profunctors. So that's where you take the free finite product category, 2 monad, so the 2 monad that produces free finite product categories. And then you do that on profunctors, take the Kleisli bicategory, and you get some fantastically abstract setting for doing algebra of different varieties, of different flavors. And this is this fantastic paper of Martin Hyland's. And this, he's been talking about this for ages. And so the work dates back to way older than 2014, but the paper came out in 2014. And I'm really glad it did, because many of us have been referring to this work as sort of, Martin vaguely told me this, and now it's there in the paper. So those are the 3 approaches. And so here's the first one involving factorization systems. So the idea is that in the desired composite theory BA, every morphism, so the morphisms are the operations, right? Every morphism would be expressed as a composite. First, an operation in A, and then an operation in B. And that, for example, for multiplication and plus, the composite 3-ary operation, so here's something in rings where you take the operation A times B plus C. You could express it first as 2 3-ary operations in the theory of monoids, A, B, and AC, followed by an operation in the theory of groups, because the distributive law says that this is the same as AB plus AC. But this is not unique, right? There are other ways you could do it. So for example, you could just randomly throw in some other operation that was totally irrelevant and then forget about it afterwards. But those are related via a projection inside the Lawvere theory. Well, inside the category F at the basis of everything. And so factorizations aren't unique. In a factorization system, usually you get a unique factorization of left map followed by right map. But here they're only unique up to morphisms in F. So we need to somehow sort of quotient out by some action of F in the middle. So, right. Strict factorization systems are distributive laws in the bicategory of spans. So this is a really nice thing because a distributive law goes from monads A, B to B, A, right? And a monad in the bicategory of spans is a category. And so we can express each of these categories as monads, and then a distributive law tells us exactly that we can take a composite of A and B and then re-express it as a composite of BA, of B followed by A followed by B, one way around or the other. And it makes BA into a monad because that's what distributive laws do, i.e. it makes BA into a category. And the category is this pullback. So the A, B, and BA are composites in the bicategory of spans, which are pullbacks. And the pullback will not a priori be a category. But if we have a distributive law, then it makes this pullback into a category. And this pullback is pastable pairs of a morphism in A followed by a morphism in B. And they've all got the same underlying objects, which is why they're pastable. And I've called them pastable rather than composable because we only know that they're composable later. So initially we just know that we can paste them next to each other. And this is really nice. It's not quite the right thing for us. The distributive law tells us how to re-express a pair one way around as a pair the other way around, but it's too strict. And so the issue is that F is in both of these categories. It's in A and it's in B. And so if we can express those uniquely, then it's too strict. And so what we need to do is quotient out by F to allow for the fact that it's in both places and we've overcounted for it. So are there any questions about that? So Roseberry and Wood define factorization systems over J, where J is a groupoid. And J being a groupoid ensures an equivalence relation on the composable pairs via J, but we don't have a groupoid, but what we can do is we can generate an equivalence relation instead, and that will account for the fact that J isn't a groupoid. So the idea is, as I said, that this pullback ignored the fact that F was in both categories, and so we're going to take this co-equalizer, where on one hand we absorb F into A, on the other hand we absorb F into B, and we take the co-equalizer to make sure that we've accounted for that being in both sides. And I use this to define factorization systems over F, which does the thing that I want it to. So the first definition, and this is a preliminary definition, is that a distributive law of Lawvere theories A over B is a factorization system over F on this composite B tends to A in span. And then the reason this is preliminary is because there's kind of a better way of saying this, because that co-equalizer looks awfully like tensoring of bimodules in span. And then it turns out bimodules of spans are profunctors. And so this is kind of transitions us into the world of profunctors. Are there any questions about that? Okay, so aside on profunctors are often, I usually see them defined directly as a profunctor from C to D is a functor from D op cross C to set. And this makes a bicategory of profunctors. So the zero cells are categories, then a one cell from C to D is a profunctor, and then a two cell is a natural transformation. So this doesn't at the moment look an awful lot like bimodules of spans, but it's the same thing really. So Benabou defined internal profunctors via bimodules. And now this is going to pile up a lot of abstraction on itself. So let's try this. So you start with a category with enough structure, which is that pullbacks and co-equalizers commute. Then you can define, you write span for the bicategory of spans in E. And then you take bimodules in that bicategory of spans. So the zero cells are monads, the one cells are bimodules, and the two cells are bimodule morphisms. And that's the definition of profunctors internal to E. And then So in the bi category of profunctors, the 0 cells are monads in span E, but monads in span E are just categories internal to E. And so then in the case E equals set, then we get bimodules of spans, and that's just the same, it turns out to be the same as profunctors. So Benabou doesn't actually make that last step, but it's clear that's what he means in his paper, I think. And then that's how we relate spans to profunctors. And then there's this appealing fact, which is that a monad in profunctors from C to C is exactly a category A equipped with an identity on object functor from C to A. So the basic idea is that a monad in Prof from C to C, if you look at the definition on the left of the screen of profunctors, it is at root a functor from C op cross C to set. And so if you take a functor from C op cross C to set, then for every pair of objects, that's giving us a set, right? And it's contravariant in the first component. So that makes it start looking like a Hom. And that is in fact going to give us the arrows from the Hom sets. And then the fact that it's actually a monad in Prof will give us the fact that we'll make that into a category. So it's not just random sets of morphisms. And then the fact that moreover, the multiplication of the monad goes via composition of profunctors, which is a coend over A. And so that coend action will tell us, I mean, it's a coend over C. So that coend action will tell us that we get a functor from C to A. The action of C will get absorbed into the category structure of A. So anyway, the point is that Lawvere theories will then arise as particular monads in Prof, where the 0 cell is F op, because we want an identity of on object's functor from F op to A. And so we can restate the definition like this, because now we've got monads somewhere. We can just say that the distributive law of Lawvere theories is, well, we did say previously that it was a factorization system over F, and now we can say that it's equivalent to a distributive law of A over B, where A and B are expressed as monads in Prof. Are there any questions about that? So the thing that is a little bit, this is more straightforward than some of the later definitions, but the thing that's a bit tricky about it is that we don't know that the composite is going to be a Lawvere theory. All we know is that the composite is going to be a monad in Prof. We don't know that it's going to be, so we know it's going to be an identity on object's functor. We don't know that it's going to preserve products. And so in order to do that, we can escalate the situation to monoidal profunctors. And so the idea is that we need Lawvere theories to be finite product preserving, and that we can build this into that construction by taking monoidal profunctors instead of just plain profunctors. So recall that profunctors internal to E were defined as bimodules in span E, and we did it in set. And so to make everything monoidal, we can now do it in monoids instead. So this is the category of monoids and monoid homomorphisms. And we now get that profunctors in mon, now we're piling everything up all over the place. Yes, it does my head in too. It's bimodules in spans in monoids. And so the thing to remember is that the 0 cells are monads in span mon. So those are internal categories in mon, and internal categories in mon are strict monoidal categories. And so this is kind of a sanity check where we do start with monoidal categories at the root of things. So now a monad in Prof mon is not just a category equipped with an identity on object's functor. It's a monoidal category equipped with an identity on object's monoidal functor. And so this has got more of the structure that we need built into it. With just an extra thing is that we don't know its product. So if the monoidal structure is product, then this thing will be finite product preserving, and then we'll be good. So this gives us the fact that Lawvere theories arise as monads on F such that the monoidal structure is in fact given by products. So we still have to restrict ourselves a little bit, but once we've done that, as long as we know that the monoidal structure is product, then any monad will automatically be a Lawvere theory. And this gives us the second definition, where a distributive law of Lawvere theories is a distributive law in the bi-category of monoidal profunctors. And this will definitely make the composite into a Lawvere theory. That is, that if A and B were finite product categories in the first place, then the composite will also be a finite product category, and we'll have a finite product preserving functor. And the proof was either you can do it directly using your bare hands or using the free finite product category 2 monad on Prof. Okay, so now, does anyone have any questions? So now we're going to ramp up to the final level of abstraction using the free finite product category on 2 monads. So that, can't speak anymore. The free finite product category 2 monad on Prof. So the next slide is a kind of peek of lots of stuff on a slide, and then it's all going to be over, I think. So if F is the free finite product category 2 monad, that means it takes a category and it produces finite products freely. That's a 2 category on cat. And the right-hand side of the slide is going to be about the abstract stuff, where this 2 monad extends to Prof, and that's the work of Martin Hyland. And then we write Prof F for that Kleisli bicategory. And this is all an abstract construction that gives us a way of expressing different flavors of theory very abstractly by changing F. So then you can just use a different 2 monad F and get a different flavor of theory sort of automatically. Then a monad on 1 in that Kleisli, right? It's a Kleisli thing. So a morphism from 1 to 1 is actually a morphism from 1 to F of 1. That's the underlying profunctor of the monad in Prof F. But what's that as a profunctor? Well, a profunctor from 1 to F of 1 is a functor from F1 op cross 1 to set. But F of 1 is the free finite product category on 1. And that's the category of finite sets, basically. And so that gives us a functor from fin set to set. But it's not just any old functor from 1, profunctor from 1 to F of 1. It's a monad. And the monad structure is going to take that functor from fin set to set and give it the structure of a finitary monad. And so this all very beautifully matches up to being a finitary monad. So what we get is that monads on 1 in Prof F are precisely Lawvere theories. And even if you don't follow the whole rest of that abstract detail, this is the key point. Because so far we've had 2 other bicategories in which Lawvere theories arise as monads, but not every monad was a Lawvere theory. So every Lawvere theory was a monad, but not every monad was a Lawvere theory. Whereas in this bicategory, it goes both ways round. Every Lawvere theory is a monad, and also every monad is a Lawvere theory. And that means as soon as we have a distributive law, we know that that composite monad will be a Lawvere theory. We don't have to do anything else to show it is one, because monads are precisely Lawvere theories. And so this is a very satisfying abstract context in which to define distributive laws for Lawvere theories. It's extremely built up on itself, and so it's, I think, quite difficult to see intuitively what's going on. Whereas in the factorization system, you could really see exactly what was going on. So this is the last definition, that a distributive law of Lawvere theories is exactly a distributive law in the bicategory Prof F. So the right-hand side of the slide is now the details of what Martin Hyland does in his paper, that notions of algebraic theory are determined by 2 monads S on cat. So this is much too fast to understand, but it's just to give you a flavor of how it works, because I think it's great. And so you start with the pre-sheaf pseudo-functor, which sends C to pre-sheaves on it. And the idea is that it's almost a monad. And so you can go around saying, well, it's almost a monad other than size issues. And if you ignore the size issues, then it's a monad and you can take the Kleisli thing for it and everything's fine. So what Martin does is he defines Kleisli structures on almost monads in a very rigorous way. And then you can define distributive laws for those things, and S extends to the Kleisli structure. And then for any S, you can define algebraic theories with respect to that S, and it's going to be monads in the Kleisli structure on the extended monad. So then if you put S being finite products, then you get Lawvere theories. Okay, so that's all in Martin's paper. Are there any questions about that? Okay, so finally, a comparison. This really abstract one gives us the way of comparing all of them. And So the claim is that these all give us the same thing, basically. And so what we're going to compare as a recap is finite tree monads on set, and then these three types of Lawvere theory, which are all monads in different settings. First, we did profunctors, then we did monoidal profunctors, and then we did this abstract Kleisli thing with the finite product category 2 monad. And there's this big diagram relating all these. Oh no. Is it back?
Yes, it's back.
Okay, good.
It's back, and we have a question.
Okay, great.
So where you say it's almost a pseudomonad other than size issues?
Yeah.
You say the rigorous definition that was done. They're asking whether it's done using relative monads.
Yes, just upper dimension.
Okay. So like something like a relative to monads, I suppose?
Yeah, yeah.
I see. Great. Thanks.
Thank you. Okay. So I think I have 2 more slides, but if it dies on the next one, I'll just stop because the last slide doesn't say anything particularly. So here is a big diagram relating all the things. Here are the 3 settings in which we're doing things. So the very abstract one is at the top. Plain monads are in the middle, and plain profunctors are in the middle, and monoidal profunctors are at the bottom. So the idea is that monads, what do monads consist of? So in the top one, they are precisely Lawvere theories. In the middle one, they're just identity on objects functors, and we're missing the finite product preserving. And on the bottom one, they're identity on objects monoidal functors. We're missing the fact that the question of whether the monoidal structure is really products. And we're relating them all to finite tree monads in just on sets. So I've restricted the objects here so that we can, I did this so that I could just do monoidal categories instead of bicategories, because that just removes one dimension and makes it easier. And because I never have to change my underlying category, I don't need to have the full bicategory structure. And so there are all these comparison functors. So from the diagonal from the left-hand side to the top is really an equivalence. That's the one saying that's really, those really match up. Then the middle one is full and faithful. And then we have the forgetful functor down on from the top right to the middle right, which is really the forgetful functor from a Kleisli to the underlying category. There's always a forgetful functor from a Kleisli category to an underlying one. And that exactly gives us the associated Lawvere theory. So that immediately tells us that if we have distributive laws in the middle right-hand version in profunctors, then the distributive law must have come from a distributive law in the top, which means that the composite monad must have come from a composite monad in the top. So it's definitely a Lawvere theory. And then there's this kind of interesting fact that I think it's interesting anyway, that the comparison functor to plain monads, to plain profunctors, the middle one, actually factors through monoidal profunctors. So everything sort of automatically is monoidal. I thought that was quite interesting. I had a referee who said it wasn't interesting at all. So I suppose it depends really what your tastes are. And then the forgetful functor just forgets the fact that we were monoidal. And so the fact that those are both full and faithful immediately gives us a correspondence between the distributive laws and also ensures that the composite we get is always going to be a Lawvere theory. So I'll dare to move to my last slide. Each of the functors send the finite tree monad to an associated Lawvere theory. Then the pseudo-functoriality makes sure that distributive laws, so this is the thing I showed right at the beginning that I said it looks like some kind of monoidal thing. It shows us that the distributive laws map to distributive laws, and the associated distributive law that we get at the end, the associated Lawvere theory we get at the end, really is the composite of the original Lawvere theories. And moreover, all the functors are full and faithful. So given any Lawvere theories on the right, any distributive law between them definitely came from one on the left because it's just a morphism. And so that morphism must have come from one on the left. So we have 3 equivalent notions of distributive law for Lawvere theories, and they correspond to the distributive laws between the associated monads. And that is my last slide, and we managed to work through our technological issues to get to the end. So that's all I have to say. And if anyone has any more questions, I'm happy to take them. Thanks very much.
Thank you so much. Thank you so much for the great talk. Okay, so let me post the paper in the chat. So we have already a question.
Mm-hmm.
If you can go back again to the relative monad thing, like the rigorous up to size issues.
Yeah.
So Todd Trimble's asking, would there be any problem if we used, instead of the pseudomonad, the small co-completion actual two monad?
So first of all, hi Todd. I didn't see you in the screen of things. Can you ask that question again? I just got distracted by a whole load more people who I didn't realize were there suddenly. It's kind of disconcerting. It's like, I don't know who was there. And then all these people, all these fantastic people. So say that again?
So the question is, if I understand it correctly, in order to avoid size issues, is it possible, instead of using the full co-completion relative monad, if one instead uses the two monad of small presheaves, so that of like small co-complete category, like categories which admit all small colimits as opposed to all colimits?
I don't know. I feel like is that going to give us, what's that going to give us for the profunctors? Because the idea is that we want morphisms from 1 to f of 1. We want morphisms from A to f of B to be profunctors, which just are functors from B op cross A to set. And so that, I feel like that just does correspond to morphisms to presheaves. But I'm not, maybe Todd has something else in mind.
I don't know, maybe something like small profunctors. Todd, do you want to clarify, or do you want to move this offline?
I'd love to. Has Todd got his video on? And I feel like I would love to find Todd in the panel of.
How you doing?
Oh, hi, Todd.
Here I am. Very nice talk. Thank you.
Thank you.
Yeah, maybe we can talk about it offline. I've been thinking a bit about small.
Okay, I'd love to talk about that.
But I think that's a relative point. But you're usually looking at bimodules, or I'm sorry, profunctors.
You're very quiet.
You're usually looking at profunctors between small categories.
Well, maybe, except that I've got finite sets.
Well, essentially small.
Yeah, essentially small. So I will fully admit that size issues are definitely not my forte, and so if you have a way of fixing that, but also I feel like I was happy to defer to Martin on this because that's what he did, but yeah, I'd be very happy to talk about that.
Okay.
All right, so we have a couple more questions. We also have a lot of comments of appreciation and virtual clapping and thank you.
Oh, thanks. Well, do those things stay in the chat? Can I have a look?
Some of them are in the YouTube chat. Some of them are somewhere else, but you can take a look.
Will they stay? Will they stay there after we finish this call?
We will save the Zoom chat.
Okay. Okay. Thanks.
So there's a question: could we adapt this to weak distributive laws on monads? So are there weak distributive laws for Lawvere theories, basically?
Good question. So the paper Cheng, Heil, and Power on pseudo-distributive laws is even longer ago than this one. And my main recollection of it is it has really huge diagrams. And so I would guess yes, if everything goes up a dimension and there's a notion of weak Lawvere theory, which I think there is. So probably. Oh, hi, Bartosz. I'm sort of belatedly looking at all the screens of people. Mm-hmm. Hi, Joachim.
We have another question, Gordon Plotkin. It's like he's saying, it would be nice to understand the distributive laws in terms of presentations as well. Would it be straightforward to see this working from factorization systems?
I don't know about straightforward, but I'd love that to happen. So Sam Staton, I don't know if he's there, but he wrote to me this morning saying that they'd done some work on this for theories, and there's a paper about that. So maybe that's relevant.
I see. That's actually pretty much the question that I wanted to ask.
Okay.
So, okay,
I mean, I would love to see something about taking a theory and seeing whether you can decompose it further, and then some theory about when something can be decomposed and when it can't. And I love that kind of stuff. Yeah.
Let's have a comment. The Clydesley by category perspective is great. There are quite a few PhDs and postdocs who are beginning to apply and expand the framework in many directions. Oh, Christian Williams.
Oh, wonderful. Who said that?
Christian Williams.
Oh,
Riverside.
thanks.
Okay, we have another question. I think it will always be that all operations from T and S will commute with each other, right?
It depends what you mean by commute. So there are various different notions of commute, and you have to get the right one. So they will all commute only in the same way that multiplication and addition commute in a ring.
So maybe the best way, sorry, yeah, go ahead.
Well, so I would say that it would be a bit strange. Okay, that was a bit judgmental. It would be not standard to say that in a ring, multiplication and addition commute with each other, I would say. I think that that's why distribute is a better term. So there is a notion of tensor product of Lawvere theory in which all the operations of one thing commute with another in a slightly different sense. And that's not what this is, because that makes things commute past each other freely. But in this case, you have a coherent way of moving some things past each other in some circumstances in one direction.
I see. Yeah, it's true.
So for example, in a two category, you can't just randomly do horizontal composition and vertical composition in a different order, depending on how you feel like it, which is what I would take commute to mean. If someone said to me, I've got horizontal composition and vertical composition and they commute, then I would take that to mean it doesn't matter which order you do them in ever. But it does matter because things have to line up in the right way, which is why the distributive law only ever goes in one direction.
I see. So I think that answers the question. So yeah,
okay.
Differently from the tensor, this is directional. That's why it's called distributive. Thank you so much.
Right. And so John Power, I can't tell who's here, so I don't know if he's here, but John Power has often said to me that he doesn't like the fact that they're called distributive laws between monads because they're a piece of extra structure. But at the level of the natural transformation, they are a piece of extra structure. But the place where they are a law is if you look at what an algebra is, because an algebra for the composite monad TS is an underlying object with an S algebra structure and a T algebra structure such that a certain diagram commutes. And the diagram that commutes is a diagram involving the lambda action, saying that the T structure and the S structure are coherent with each other. And so they don't just, it's not that they all commute with each other, it's that under certain circumstances, there's a way of re-expressing them. And it is that if you do one of them before the other, there's a way of moving it past. But it really is a piece of extra structure that tells us how to move them past each other, not just that they work in both directions.
I see that. So that in that sense, it's a law. Like it's not just a map, but also a commutative diagram involving it.
Yeah. So it's kind of a law at the level of the theories, even though it's a map. I mean, it's a law at the level of the algebras, even though it's a map at the level of the theories.
I see. Yeah. Yeah. Yes. Good. Good. Yeah, that's a good way to see it.
My Zoom screen is telling me that you're David Spivak. It's a little bit disconcerting.
Really? Oh no, no. Oh, have I become my own boss already? Wow, my career is crazy. We have another question.
Mm-hmm.
Valeria Paiva.
Oh, hi.
says, very nice, Eugenia, thanks. Question. What about monads not associated to Lawvere theories? Can we have a version of the last triangle?
Monads not associated to Lawvere theories. I'm not sure So do you want to speak, Valeria?
Valeria Jupaiva, could you please clarify? You're free to unmute yourself.
Oh, no, I can't.
Hello.
Hello.
Yeah, we.
Great. Was very, very nice. What I meant was that if I understand it, if I understand it at all, we are kind of doing this stuff for Lawvere theories. So it's all about ends and things that you can do over that. But you know, in programming we have other monads that we want to deal with, and I was wondering if there would be some sort of generalization that we could think about, because the three different presentations, they don't, I mean, I don't know, as you're saying, it uses very strongly the finite product somewhere, but you know, maybe it is more general than that. Maybe we actually can have something about generic monads, kind of going in the direction of Ross Street's categories of monads.
So yes, whenever you have monads, you can look for distributive laws between them. And Martin's paper shows all sorts of different ways that you can replace the finite product monad with other things to get different kinds of theory, and then everything would work inside there. Then it would be interesting to see. So that's the abstract place where it's very easy to make a generalization, because you just replace F, the finite product monad, with something else, and then seeing what it gives you in a more concrete place like factorization systems would be interesting. Yeah, I don't know. I think
that's what I meant by looking at the last triangle that you had. So is
so the bottom part, right? So if you replace the curly F by something else, then what do you get?
Yes.
Down there. Yeah, that would be interesting. So the bottom monoidal profunctors was inspired by Steve Lack's work on composing props. And for props, you use finite sets and bijections. And so there's some other possibilities in Steve's paper.
Indeed. Very interesting. Thank you.
Thanks.
And you know, one more thing is that just the computer, you shouldn't worry about the computer freezing up, because it just gave people some more time to think about what was happening, because it was a very beautiful but very fast talk.
Okay, thank you.
Yeah, somebody on Zulip also said that they were happy the internet was down for a moment so they could look up on Wikipedia some of the things.
Oh,
they wouldn't
okay.
have been able to follow otherwise.
Okay, good.
We have a comment by Walter Tolan that says, hopefully Bill will have a chance to see your slides. It's a great way to reconcile his theories and monads. So I suppose Bill is Bill Lawvere.
Thanks. There's something, I'm feeling very moved about everyone who's here, because it's kind of, because we didn't get to have a CT conference. But this is a really amazing way that people from all over the place can sort of all have a conversation. Thanks.
Yeah, I like it a lot too.
And there's also, nice I mean, there's a bunch of people who don't often come to CTs as well. So yeah, thanks.
Yeah, it's true. It's exciting to see so many people that sometimes you just read books of, or that you see online, like mentioned on the Lab somewhere, and they're suddenly here participating in a conversation. It's beautiful. Okay, are there any more questions or comments for Eugenia? No, there are more thank you comments, which are always very pleasant to hear.
That is nice.
And of course, if anybody comes up with a question at some point, feel free to ask in the Zolib thread. Let me post the link in the chat. And I say for now, let's stop the recording and streaming, but let's first thank our speaker again. Thanks a lot. Gigi was very interesting.
Thanks everyone, and thanks for the opportunity. Thank you.